Having completed the great task of problem 17b, I thought we could chop off a lot of the problems in one go here. Describe the zeros. I actually already showed you that. Unfortunately, there were errors in my computations, but somehow the result was right. I'll just show you the result first. There we go. So, f has a zero at infinity and no other. Of course, they can only have 1 0, each of them. And here they are non-zero both. And the cusp I've got as the expansions as well. The calculation, I used this lovely formula, which can be applied for many nice purposes. I've today particularly used it with A1, meaning S, and then I needed this formula dealing with the composition of translations, so the commutativity. And as an example, I'll just show you what I did. I don't know if it was this morning or whether it was yesterday afternoon, but that's to compute the value at the cusps of capital F. We need to transform eta of 4z, and using the formula we end up with eta of composed with t halves, so that's eta of z plus 1 half, and then we use the formula for that. I made a mistake thinking I could do something else. I knew it was wrong, but I'd done it anyway, so I must have been tired that day. But now I come through and get the result you just saw. So let's assume we have f in M2 gamma naught of 4. It will have a 0 because the sum of the zeros, or the order of the zeros, is unity, and when k is 2, that's the result of problem 17b. And then we can define a function so it's a linear combination of theta to the 4th and f. And of course, when z equals z naught, then the determinant vanishes. And it's obviously a modular form of gamma naught of 4, as it's a linear space over C. And it's the only 0 it has. Oh, so is f, so we could divide either by either. And that means it's a constant. So that proves that. We can generalize that. Oh, I forgot. That was now that's weird. If k is smaller than 1, or I didn't know we had negative k's now. Let's write it a different way. K smaller than 2 and not naught. Then there are no zeros, but the constants are not modular forms except when k is naught. So the only function that has where we can't use the k half, that's the null function, so that works. So that's the null space. And then when we come to k equals 2k naught, that's f. So we are in the even positive numbers. Then we have k naught zeros. And for each of them we define this function. And that's set I is the only zero of this function, and then we can divide again. So that's not interesting. And it will of course give a homogeneous polynomial. And the degree is just the number of zeros, that's k naught. Right. We should actually be able to write up the a formula for the dimension of it. Let's do that. So it's it's generated by the homogeneous monomials. So it's f to some power and that's trivial. That's trivial. That's silly. Now, G. Yes, M6. That's the first one where we have possibility of 3 zeros and we have 3 cusps. So that's where we can have the first cusp form. You can see f is 2 to minus 6 and theta is 2 to minus 4th. Second, which means that this one is 16 times as large as that. So we have to say f minus of 16.5 minus f phi, no, this is the one, 16f minus phi to fourth. I'll just write it up. That has a 0 at z equals naught. And we can just write up the Q expansion. 4q4 plus, etc., just the leading term. So it's a 0 of order 1. Interesting enough. I can't really get used to it. And then multiplying the three functions, that gives this. Gives us a cusp form. That was G. This one seems a little difficult. This seems also rather silly. If we have f, let's do it. That means it has zeros at the three cusps. And the product, where do we have it? It isn't called anything. That lies in S6, and that means that f divided by this guy lies in, we don't know if it's in M. K minus 6 of gamma naught of 4. Now, what was I about to show here? Yes, we already know that it can be written as a homogeneous polynomial of degree k naught. So the only thing is that it can be divisible by this, but this follows from the fact that it's a modular form of order k minus 6, so there's nothing more. That's like by induction. So the only one that is not obvious is problem 17H. What bothered me when I read problem H was that these etas, they do not have many zeros, I thought. But then when I stopped recording, I realized that eta to 24th has zeros at every cusp, because it's the delta function. Oops. And that's why when we take the fractions of the zeros, like in F and in theta, then a lot of the zeros cancel. All right. So it's just a question of whether or not it satisfies the transformation formula. And that's just a question of testing it. So the function was eta of 2z, and we have eta z to s 1/2 equals I to minus 1/2 eta of z. And the generator of gamma 2, that's t squared, and s t squared s, whatever, it's one of them. So let's get the show on the road. It's 2 to minus 1/2 I to minus 1/2 eta composed with the reciprocal of 2 and then t squared, and then we still need to operate with s on it. And this gives eta with t to first and this is the 24th root of unity times eta You see, I'm beginning to get proficient at this algebra. So this 1/2 to minus 1/2, I to minus 1/2, eta 2. So cancel. Oh, that was not the one. These two cancel. So we end up to I minus first xi eta 0.2. And that means if we put it to the, it was the 12th power. And this becomes order 6. I to the 12th, that's unity. And xi to the 12th, that's minus unity. So it changes sign, which means that this does not lie in M6 of gamma of 2. But if we write 4 here, it's to the 4th, and that means it's to the 2nd. That means we get xi squared. And that means we get a plus here. So that means that it is actually that was to the 12th. That should be black. But it actually lies in M6 of gamma naught of 4. And as I already mentioned, it's a cusp form. So we just need to see how it behaves at infinity. So it's Q24th, but it's squared. Oops. and that means that eta to the 12th, the function to the 12th, that becomes q. So that means it goes as q and the cusp form we have, now what was that? Theta to the 8th f minus 16 theta to the 4th capital F. So we need to find out how that goes. So this one goes like 1 plus 8q. That needs to be squared. And f, that's q times 1 plus 4q squared. Then minus 16. And then this is q squared. No, that's 1 plus 8q. And then it's f squared. We didn't need all that because it's clear already here that the first term is q, and then it becomes a little complicated. Minus 16q squared, and here we get 16. Oh, it seems that that vanishes. Well, never mind. Q is the first term, and that means that they are not only proportional, the constant of proportionality is actually unity. So that was h. I was thinking about writing up the power series equation, but that has been interesting in the other cases. And I think this one would be interesting as well, but I don't think I'll report that, so I'll just finish here.